Hi everybody, I'd like to show you a little video about an Edison circuit and what happens to all the values when a fuse blows. Over here I have a typical Edison circuit. The R1 resistance is receiving 120 volts. We can put that here. The R3 value is across all of the 240 volts of that supply, and R2 over here is also getting 120 volts. So if I go with P equals I times E, I can divide 1200 times 120, and that will give me a 10 amp current flow through R1. 1800 watts divided by 120 volts will give me a 15 amp flow, and 2400 divided by 240 gets me 10 amps out here. One thing that we can look at is, so this is before the fuse blows, we can actually determine what the neutral current will be. And the neutral current is here. One thing that people don't quite think about when they think about an Edison circuit is ahead of all of this, you have a transformer. And that transformer has a center tap where your neutral is. Now, if you think about the polarity, if I grab an instantaneous polarity and give line 1 a negative, and down here line 2 a positive, what happens is as we move across these windings, the polarity moves from very, very negative to more positive here, and then it keeps moving from the negative up and through here, and by the time we get here, we're very positive. So you could look at this as being very, very positive, this as being very, very negative. In between here, this center point here at the negative is more negative than this very positive piece, but it also is more positive than this negative piece. So if we look at the current flow, what ends up happening is we have some current coming out of the negative going to the positive in that 120 volt loop, and then coming out of this negative and going back this way. So out of the negative in the center to back to line 2. You notice in here in the middle, in the neutral, I will have 10 amps flowing this direction in the top loop and 15 amps flowing this way in the bottom loop. And what happens is we have a 5 amp current flow in the neutral, the difference between those two. So that's before the fuse breaks. The overall current, of course, would be a little bit different because we have to look at Kirchhoff's current law. And so if there's 10 amps flowing off to that load out here, and we had 10 amps flowing around because of this, then at this junction, we would have had 10 amps flowing down there, and at this point, we would have had 20 amps. So 20 amps flowing into the junction, 10 that way, 10 that way. This 10 amps coming back will join the 15 amps coming around in this loop. And flowing back, we have 25 amps out of that node flowing back. And you'll notice that there's 20 amps flowing out there, 25 flowing back. We're missing 5 amps going out, and that 5 amps then we know is going that direction. So the next thing is, what happens if fuse A blows? And so what happens is we end up with a completely different circuit. If you notice, when I come out of the neutral, get to this junction, I can go 2 ways. So I can go through R2, which would give me sort of the normal path we would expect for R2, line 2, so out of the neutral, 120 volts, comes through, and we're going through R2, and R2 doesn't change. It was getting 120 volts, and it still is getting 120 volts. Well, the interesting part is the current comes out of neutral, and it also heads up here. So now it's actually flowing against the current that was supposed to be going in that clockwise loop. And when it gets over here, it goes over here, down and back. So in the second part of this circuit, we come out to the junction, then we go and turn and go through R1, and then we keep going around here and go through R3 and back to 120 volts. Now we end up with quite a different looking circuit. This is a combination circuit instead of an Edison circuit. A little tip, whenever we lose a neutral or lose a fuse, our voltages are all going to change at each one of these loads. And so the only thing that we can take down into the new circuit is the resistance. So what I have to do is go back up to my original circuit where everything was working, and I have to divide things out. 120 volts divided by 10 would give me 12 ohms there. 120 volts divided by 15 would give me 8 ohms there, and 240 divided by 10 would give me 24 ohms there. So now I can populate these T's down here. My R2 was actually 8 ohms. R1 is 12 ohms, and R3 is 24 ohms. Because it's a combination circuit, I'm going to have to add these two together and get an equivalent T for them. So because they're in series, I can just add them. So that's 36 ohms in this branch 2, we'll call it, and it's getting access to all of the 120 volts. Doesn't see 240 volts anymore. 120 volts across that equivalent T gives me 3.3 amps down this branch. So because these are in series, each one of those will get 3.3 amps. And now I have two numbers in there, calculated those out already. So we have 80 volts on the bottom one and 40 volts on the top one. And like I mentioned before, this has not changed. So that guy stays the same. Now, what I have to figure out is what's actually happening, and what would happen if I put a voltmeter across this fuse. How much would the voltmeter read? And the tricky part is that I can use Kirchhoff's current law around any closed loop, or actually Kirchhoff's voltage law, which says around the algebraic sum around any closed loop has to equal 0. So if I look at this closed loop, it's being closed by the voltmeter. Now the voltmeter has a huge amount of resistance. So there's really just a very minute amount of current flowing through the voltmeter to cause the meter movement to move. Usually it's in the range of like 50 microamps. Not going to actually drive the load, give us any voltage drop. And so what ends up happening is these voltages are all gone, and I now have these voltages. And so I'm going to put that over here. We have the fuse that is blowing. We come out to our neutral. And let's look. Remember I said that we had 120 volts. It's coming out of here. It's going up this direction. It's also splitting and going down that direction. Comes around, goes down through there. And these arrows are a key piece to this, solving this. So I can take any closed loop. Remember the instantaneous value over here. I had picked a negative, which meant my loops were going to go clockwise, out of the negative into the positive, out of the negative into the positive. I'm going to do the same thing. We're going to pick instantaneous values. And now we're going to use Kirchhoff's voltage law to solve this. To do that, I got to repopulate these with the voltages. So R2 down here was 120 volts. This was R1, and it was now 40 volts. And R3, which is out here with the new voltage, was 80 volts. And so what we have to do now is pick around any closed loop. And I'm just going to pick this one to start with. I'll do more than one. They'll all come out to be the same thing. So our voltage supply of 120 is a rise. We don't know what the voltage across this voltmeter, across this fuse will be. So I'm going to put a little question mark there. And then I'm going to add this voltage drop. But just pay attention to this arrow because it's not a voltage drop. This arrow is actually opposing my current flow in that circuit. And so it's going to be a voltage rise. So I would add plus 40 volts for that. And that whole thing has to equal 0 for Kirchhoff's voltage law. So I had a positive 120 and a positive 40 plus something else. We're going to end up with 160 volts across this voltmeter. Now let's try it another way and see if we get the same thing. So this time I'm going to take the big loop out here. And in this case, I'm starting with 240 volts because we have the advantage of being from line 1 to line 2. So the whole 240 volts is in play. And that's a positive supply volt. When I come across here, it's a unknown voltage at the voltmeter. Then I come out here. Notice that this arrow, current flow through the actual 80 volt load, is in the same direction as my instantaneous. And that means that this is going to be a drop. So plus a negative 80 volts and nothing else before we get back to line 2. So all of that has to equal 0. So I had 240 minus 80 gives me a difference of 160 volts. And that again tells me that my voltmeter is going to read 160. Thank you very much for watching. Have a great day.